So in our last video, we figured out what the control signal needed to be to make the move reg immediate happen. And like I said, you're going to have to figure out what all the control signals are for each of the different instructions. Now, how does this relate to the timing diagram that we were working on? So I've added a couple more signals to the timing diagram, the ones that we have noticed that we're going to need for the move instruction. I've also added registers R10 and R11 so you can see how they get affected as we go through the timing diagram. Okay, first off, remember all the yellow signals are control signals. So in the init state, all of our control signals are 0, and we can verify that by seeing that in our process we set everything to 0. And when we're in the init state, the only thing we set was to 1 was the reset. So everything else remained 0. So that means all these control signals are going to be 0 in the init state. And we haven't put anything into our registers yet, and you probably did the others get 0 thing. So register R10 is going to be hex 00, and register R11 is initially going to be hex 00. Okay, so that puts us into the fetch state. How do you figure out what all these signals are in the fetch state? Well, again, nothing happens in the fetch state. The only thing that happens in the fetch state is PC Inc is 1. Every other control signal is 0. So we can go ahead and make sure all of our control signals are 0 in our timing diagram. So ALU select is 4 zeros. It's not letting you draw 4 zeros, but everything's 0. And nothing has happened to the registers yet, so they're going to stay as 0. I guess that did something weird to the column width, so I'm going to say type it in again. Okay, now we are in the execute state. We are in the execute state of the move. So we already figured out ALU select had to be the value for the move instruction. So you figure this out again by going to your handy dandy VHDL that you've already done, going to the execute state, going down to the move and seeing, oh, ALU select is going to be 1110. So that's what I'm going to see here. 1110. ALU op Y select better be a 1. RF write we decided had to be a 1 because we're writing. And RF OE we decided needed to be a 0 because we didn't need to read register X. The registers themselves do not change yet, because notice that the write signal is a 1 here, but it's not going to be able to get activated until the rising edge of the clock, which I've represented by this column gray bar here. Remember, that's the rising edge. So even though we say we're setting the write signal to a 1, remember the write is synchronous with the clock, so the write will not happen until the clock edge. So the registers are still going to remain 0. However, at the clock edge, because the RF write signal is a 1, and we're writing to R10, R10 is going to change to 0xAB in the very following cycle as a result of that write being a 1. R11 isn't changing yet, because we're just doing this first move instruction. In a fetch cycle, it's really easy. All the control signals are 0. We already determined that. So I'm just going to go ahead and put those in all the remaining fetch cycles. Only control signal that's 1 in a fetch cycle is the PC Inc signal. Alright, so we got to figure out what happened to the rest of this stuff. So, here we decided that we are now doing a move instruction again. So we did the first move, and now we're in the execute cycle of the second move. So because it's the same type of instruction, the control signals are all going to be the same. Because we did one move here, now we're just going to do another move. The same register values are going to be here because we haven't written anything yet. But now because of this register write, we're going to go ahead and write to register, what register? Register 11. So now as a result, registers 10 stayed the same, but because we did a write in this move cycle, we're going to get register 11 to be hex 11. Okay, so now we are in the execute cycle for the sub instruction. And we have to figure out, what does the sub need? Well, the sub is going to need the selector to be whatever the sub instruction is. So we can get that from our architecture diagram. Sub is 0010. Guess I can put that in quotes so you can see it all. 0010 is what you'll see. ALU op Y select. This is a sub reg instruction. So ALU op Y is going to have to be a 1. So, sorry, not a 1, a 0, because it's going to get the value coming out of the register. So it's going to be a 0. Register write needs to be a 1, because when we're done with this sub instruction, we want it to write into R10. And RFOE also needs to be a 1, because in this case, our X register, R10, we need to read it because we want it to come out of this tri-state in order to go into the ALU, so the ALU can take A and subtract it from B. So that needs to be a 1. And so notice these are the signals that you would then write into your case for the sub instruction. And there might be some others that we haven't put in this list. Okay, so now let's see what happens. So we have register R10 and R11. Nothing has changed them, so they're going to stay the same. But now, in the following cycle, because we set this write to a 1, what register is going to get changed? R10 is going to get changed because we're performing this sub. What value is it going to have? It's going to have R10 minus R11, so it's going to have AB minus 1, 1, which is going to be 9A. Will get put back into R10, and R11 stays the same. The next execute instruction is 0. And so what's going to happen if we have if we have a 0 instruction? We have nothing. Nothing's going to happen. And so what would happen is that would fall into the when others case, because it doesn't match any of the opcodes for the instructions that we want to do. And so in the when others case, we just go to the next fetch state. And that means since we didn't set anything to 1, everything's going to remain a 0. So all of these signals, control signals, are going to remain a 0 in the execute state for this 0 instruction, and the registers will not change, and they'll stay the same. And that's what's going to happen for the rest of the program, because there's no other instructions in the program until the program counter rolls over from 1023 back down to 0, and then it will start over again. So I hope this example has helped you to see what's going on in the machine. So now, how is this all going to fit together in your lab? If you look at the instructions for Lab 7, it's got 5 different parts. The first part states the architecture diagram. So I highly recommend that you take the existing architecture diagram as we've been looking at it and make your own. So this is a great start, but it is very possible that maybe in the unit you created, maybe you decided to call this sum instead of result, or maybe you decided to call the reg file my reg file, or whatever names you wanted to use. It is super critical that your names in your overall diagram match your names in your specific units that you've created. Now, if you've been following the lab exactly and following the name formats, then you probably just basically have this picture. But the other thing that's useful about making your own diagram is also labeling all these intermediate signals. Because if you want to do port mapping, you will have to go ahead and connect these signals to connect all these units by giving them intermediate signal names to connect them. So it might be helpful to label all these intermediate signals on a piece of paper so you don't get it confused when you're doing all of your port mapping. So that's part 1, and remember, we're not doing the stack pointer or the scratch RAM for this lab. Within that, you're going to have 2 flag registers. So this flags box you can see is actually this dotted line over here. So this is what you're going to do. I gave you on Polylearn a flag register VHDL file. All you're going to have to do is add that file into your project of the entire RAT CPU, and then you'll have to have 2 instances of it, one for the carry and one for the 0 flag. Okay, so that's part 1. Part 2 is the program. So for this lab, you're going to generate the program based upon this assembly code. So this is the assembly code that you want to have running. And what's really cool is you're going to be able to test to see if this works on your Nexus board. So you're actually going to see your CPU running through your Nexus board, which is really awesome. It's going to get a value from the switches. It's going to move the value 1 into R11. Then it will subtract 1 from R10. So whatever you had on the switches, let's say you had the value of 8 on the switches. It subtracts 1, so it gets 7. And then it outputs the number 7 to the LEDs. And so you would see if your switches are 1, 0, 0, 0, what you're going to see on the lights is 0, 1, 1, 1, because that's 7. And then it branches back and reads your switches again, and you can change your switches, and it will subtract. And it does that over and over again. So what you need to do is go to RATSim, type this up, hit assemble, and grab the program. The third part is designing your control unit, which is what we've spent the last 50 minutes or so discussing. You need to go ahead and fill in the control unit signals for all the instructions we have listed here, branch, sub, in and out. We did the move together, so I already made it easier for you. So you have to figure out what the control signals are for each of these instructions and fill them in. It says you also need to do the states fetch and reset, but that's already been done for you, so you don't need to worry about that. It talks about this spreadsheet, which I used to give in the past, but I think it's more confusing than it needs to be, so don't worry about the spreadsheet. The part 4 is creating the RAT CPU. It's also called the MCU for microcontroller unit. And this is just putting everything together. So if you look at this diagram, let me pull it up for you. This sort of gives you an idea. The RAT CPU is going to be a file that connects the PC, the program, the control unit, the ALU, the register file, and the 2 flag registers. So you're going to have all of these. These are all separate files, your PC.vhd, your program.vhd, your ALU.vhd. These are all files that you're going to add to your project, and then you're going to make a RAT CPU file that connects all of them. Now I know some of you like using the schematic editor, and you're welcome to do that to make all your connections, or you're welcome to use structural modeling using the port mapping command to connect everything. And how are you going to connect everything? Well, it's going to look just like this picture here. And remember, part 1 was you could draw your own picture and write your own intermediate signals and connect everything based on the picture. So that's the next part. The last part is the RAT wrapper. And what is the RAT wrapper? This is the thing that goes around the CPU. So back to this picture, see the RAT wrapper goes around the CPU. And what the RAT wrapper is going to allow us to do is connect to different IOs. In this lab, we're going to just do a very simple IO, which is the switches and LEDs on the Nexus 2 board, and I've provided the RAT wrapper for you. So all you have to do is include the RAT wrapper in your project and make it the top module, and everything should run just fine for you when you want to test it on your board. We'll go over the RAT wrapper in more detail later on in this course, but for now you can just go ahead and use it to connect it to your switches and LEDs. So then once you add all these files to your project and your RAT wrapper is the topmost file, you can create a constraints file for your switches and your LEDs, and you can go ahead and run it on your board. So there's the picture again, then there's questions to answer, and the deliverables are that I want to see an ISIM printout showing the correct functionality of your CPU program. So that's going to look very similar to this Excel file that we've been working on, but not for these instructions, but for the ones that you're doing for the lab. And the easiest way to do that is to create a test bench for the CPU and not for the wrapper, because the wrapper is just going to show you the switches and LEDs. It's not going to show you all the inner workings of the CPU. So go ahead and create a test bench for the CPU to be able to see how all those signals change throughout. Alright, I hope that gives you a good start, and good luck on Lab 7.